we'll continue our introduction of linear programming using the Galaxy industry. So earlier we have explained what the mathematical model is, which are typed nicely and enclosed in this red box. So what the mathematical model does essentially is to translate this Galaxy case study, which was described using words, into the language of algebra. So we use two variables, x1 and x2, to denote the unknown quantity of space rays and zapper respectively. And we use this expression to quantify the total profit associated with x1, x2 amounts of each product. And we also further stipulate we want to maximize this total profit. And we use 4 inequality to capture the 4 physical constraints that are present in the Galaxy industry example. So that is mathematical model. Now the next step is we need to actually solve for x1 and x2, meaning to find out the particular values of dozens of space rays and dozens of zappers to produce so that we can maximize the profit, which requires the graphical analysis. And what graphical analysis does essentially is another round of translation from algebra to geometry. And that's why I draw this two-dimensional Cartesian coordinate system here. Let's now first look at how to interpret or translate decision variable. Here I use dB to abbreviate decision variable into geometric representation. So earlier our first option, if you recall from earlier video, option 1 calls for manufacturing 500 dozens of space rays and no zapper. So as you know, in a two-dimensional coordinate representation, these two numbers which form a pair can be represented as one point. So x1 in this case representing number of dozens of space rays, x2 number of dozens of zappers. So we can find the corresponding point. So x1 equal to 500, x2 equal to 0 here. So this point, let's use another color. So here 500 and 0, the option 1, the solution, the production plan for option 1 will be represented as this point right here at 500, 0. So similarly, we can represent the solution from option 2. Again, recall this x1 equal to 450, x2 equal to 100. So similarly, to find that point in this two-dimensional coordinate system is to find where x1 will be somewhere here, x2 is 100, somewhere here, so it will be a point about here. Again, here we don't need to worry about being drawn to scale. So this point, the coordinate will be 450, 100. So now if I ask you, what is the meaning of this point? So let's say the coordinate of this point is 1000 and 600, 700 for x2. So the physical meaning under the context of this Galois example for this point will become a production plan that produces x1 1000 dozens and x2 700 dozens. So let's say option 3. Now that is the meaning of decision variable represented in a graphical or geometric representation. Now let's move on to discuss what is the geometric representation of constraints. Notice I skipped objective function, which will be discussed in the next video. We'll first look at the first inequality here. We look at firstly the first inequality, which conveys the physical constraint that we only have 1,000 pounds of plastic available for production. So in order to understand the geometric meaning of an inequality, we need to first understand its associated equation. So its associated equation will be 2x1 plus x2 equal to 1,000. And we all know this is the representation of a straight line. And a straight line is defined by 2 points. So we just need to find 2 distinct points so we can locate this line in this two-dimensional coordinate system. How do we do that? We can arbitrarily choose any x1 value and use this equation to solve for x2. That will give us 1 point. And we can again arbitrarily select a different value for x1 and then again solve for x2. That will give us the x2 value for the second point. But of course, the easiest way is set x1 equal to 0. And once we have x1 equal to 0, then we, using this equation, we can solve for x2, which would be 1,000. And this time we will set x2 equal to 0 in order for x2 equal to 0 and still make the two sides of the equation equal to each other. X1 has to be equal to 500. So this one will be our first point, and this one is our second point. Remember, as long as you can find 2 distinct points, you can always find a line. The reason we use 0 here is to make the computation easier. Now, so the first point is 0, 1,000, which will be 0 from x1, 1,000 here. Okay, let me change to a different color. So that will be here. This will be the first point we have identified. The second point will be x1 equal to 500 here, and then x2 equal to 0, which is this point. So the line that is represented by this equation will be the line that goes through both points. So let's find the line. So this is a line that is equivalent to this equation. So let me write down the equation here, right next to the line, equal to 1,000. So this equation is associated with two inequality. The first one is less than 1,000. The second one is greater than 1,000. This line, this green line, which is this first equation, divides the two-dimensional space into two half spaces. And it turns out that one of the half, let's call this side half space 1. Let me change to a different color. So let's call this side a half space 1. Let's call this side a half space 2. So one of the inequality corresponds to one of the two half space. The other one corresponds to the other one half space. So our task now is to figure out which one is which one. And the easiest way is to pick any random point from one of the half spaces and to see which of the two inequality that point will satisfy. By satisfy, I mean if I plug in two numbers into this first inequality, let's call this the left-hand side of the inequality. If this point satisfies this inequality, meaning the sum of the left-hand side will be less than 1,000, which we would denote as right-hand side. So let's just try it. Let's just pick this point that we discussed earlier. Let's try 2 times 1,000 plus 700, which is 2,700, which is greater than 1,000. Therefore, this point does not satisfy the first inequality. That makes it satisfy the second inequality. So now we know this the second inequality corresponding to the half space 2, whereas the first inequality represents the half space 1. You can also verify it by picking an arbitrary point from half space 1 to see whether or not it indeed satisfies the first inequality. Let's again arbitrarily pick a point from the half space 1, and of course we can always pick origin because it's 0 and 0, so that will make the calculation really easy. Try it again. So 2 times 0 plus 0 equal to 0, of course, is less than 1,000. So this confirms our previous finding that the first half space 1 is indeed represented by this inequality. I also want to quickly point out something. So if you are thinking that the reason this first inequality is corresponding to the half space 1 is because the half space 1 is underneath the line. So in other words, if you are thinking that less than is always corresponding to the area, the half space that is beneath the line, then it will be incorrect, because for this inequality I can multiply both sides by -1, so it will become greater than -1,000. So realize the sign itself is arbitrary. So the only trial and true method is to find a point from either side and to actually test it out to see whether or not the left hand side is less than the right hand side. So now we finally get to the point that we can answer what is the meaning of this inequality that also includes the equal sign. So it will be the two combined. So the geometric representation of this inequality will be the half space 1 plus the line itself. So now let's think about the question whether or not the option 3 we proposed earlier is a feasible production plan. So here again, 1,700 means we are trying to produce 1,000 dozens of space ray and 700 dozens of zappers. And again here, the plastic required to produce that many dozens will be way more than 1,000. Therefore, this production plan is not feasible, and same is true with any production plans that lies in the half space 2. So just considering this one constraint alone, let me change to a different color again. Just to consider this one constraint alone, we know only the production plan that lies in the half space 1 is feasible. So similarly, we could apply the same method to try to identify the geometric representation that corresponding to the second inequality. And I will leave it for you to try yourself, but I will show you where the line is located. Let's still use the color green, and it will locate it between these 2 points. Let's pick a line. It will locate between this point and here, about 800. So similarly, you can identify which of the two sides satisfies this inequality. And again, by using the method I described earlier, you can also identify that this side corresponding to the feasible region. And again, following the same approach, we know x1 greater or equal to 0 indicates the half space above this horizontal axis, and x2 greater or equal to 0 corresponds to the half space to the right, to the vertical axis. So the overlapping area, by applying all the 4 constraints, now becomes this polygon surrounded by 4 edges. Let me tidy up this graph a little bit before I introduce a few new terminology. Again, this coordinates is actually for this point here. Now, okay, so we call this region that is surrounded by the 4 edges the feasible region. Because all the feasible solution, in the context of the galaxy example, all the feasible mixture of 2 products lied within this region, including the 4 edges, because only these points can satisfy all the constraints. So, and then we call, let me again change to a different color. we call this any point that lies within the region interior point. Interior point. And then we call those point that lies on the edge a boundary point. A boundary point. And then we call this corner. Those points that lie at the intersection of two lines as extreme point. So these are the new terminology we need to familiarize. Now we are one step closer to finding the actual optimal solution, but we will talk about that in the next segment, which requires the understanding of the geometric representation of objective function that we haven't had time to discuss here.